Good day, everyone. So today we'll be looking at questions and answers on gravitational field, calculation questions precisely. All right. Without much ado, let's dive into this. All right. Let's take an example one here. The question says two spheres of masses 100 kilogram and 90 kilogram, respectively, have their centers separated by a distance of 1.0 meters. Calculate the magnitude of the force of attraction between them, given that the gravitational constant is 6.70 times 10 raised to the power minus 11 Newton meter square per kilogram square. Okay, very simple. Now, usual practice, we write out the parameters given. All right, so two sphere of mass is 100 kilogram and 90 kilogram. I write that mass 1 is 100 kilogram, mass 2 is 90 kilogram. Then these two masses are separated by a distance of 1.0 meters, meaning that our r, which is the distance, is 1.0. Okay, is 1.0 meters. Okay. All right, and then we have to calculate the magnitude of the force of attraction. So we are looking for the unknown, that's the F. All right, so from the law of gravitational, Newton's law of gravitational force, we have this equation that is F equals G m1 m2 over r squared. Okay, now all we need to do is to substitute all the values given to us and find the value of F. So we have our G as a constant here. So we substitute the value of G, which is 6.70 times 10 raised to the power minus 11. 10 raised to the power minus 11. Yeah. So that is the first thing we need to do. We need to substitute our values. 10 raised to the power minus 11. Okay, that's then we are giving mass m1, that's times 100 times 90, that's m1, m2, all over 1 square because our r is 1, so 1 squared. So when you simplify all of these, we'll find out that the force of attraction is 6.03 times 10 raised to the power minus 7 Newton. Very straightforward. All right. Okay, let's take another example on this. Okay, example 2. Here it says a force of 200 Newton acts between two objects at a certain distance apart. The value of the force when the distance is halved is what? Okay, very simple too. We are given the force here to be 200 Newton. That's F1 is 200 Newton. Now we are having F1, which is initial force, because the distance has been reduced to half. So we need to get the second force. What will now be the force of attraction between them when the distance between the two objects has been reduced? That's why we have F1 now. Before the reduction of the distance, F1, which is 200 Newton. Then we have to find the new force of attraction if the distance, which is represented by R2, is now half of the distance when it was when the force was 200 Newton. Now, when the force was 200 Newton, the distance is R1. But when the force is now, when the distance between them is now R2, which equal to R1 over R1 over 2, then what will now be the new force? So if the distance is reduced to half of the initial distance, then that means R2 is equal to half of R1. And when you multiply this, you'll be having multiply 2 by R2, you're having 2R2 to be equal to R1. So here we could see that 2R2 equals to R1. Now, from the equation, we can also say the formula is F1 R1 squared equals F2 R2 squared. F1 is the initial force, R1 is the initial distance between them before it was reduced to half, F2 is the final force after it has been reduced, after the distance has been reduced to half, and R2 is the new distance that we have. Okay, and we have seen here that by relationship 2R2 equals R1. Okay, now substituting our value into this equation, our F1 is 200, that's 200, multiplied by our R1. Now note that our R1 is now 2R2. So instead of writing R1, we replace R1 with 2R2, then the square still remains. So 2R2 all squared equals our F2 is what we are looking for. That's F2 repeated here, and then our R2 squared is also repeated. Right? So going further, 200 still brought down, multiplied by, now when you expand this, this will be 2 square, and 2 square will give us 4, and also R2 squared. So that's why we have 4R2 squared, yeah, equals F2 R2 squared. Now when you simplify this, R2 squared will cancel R2 squared, and our F2 will now be 200 times 4, which is giving us 800 newtons. Okay, let's take another example. This question says, the gravitational force between two objects of masses 10 to the power 24 and 10 to the power 27 is 6.67 newton. Calculate the distance between them, given that the gravitational constant is 6.67 times 10 to the power minus 11 Newton meter square per kilogram squared. Very simple. Writing out our parameters here, we are given the masses. So M1 is 10 to the power 24, M2 is 10 to the power 27. The force of attraction between them is given to be 6.67 Newton, and we have to calculate the distance between them, which is R. R equals to unknown. Now, from the formula, the distance between them by formula will be the square root of G M1 M2 over F. Okay, and that's equal to the square root. Substituting the value of G, which is given in the question as a constant, we have 6.67 times 10 to the power minus 11 multiplied by M1, which is 10 to the power 24, and M2, which is 10 to the power 27, all over F, which is 6.67. And here, when you simplify with a calculator, 6.67 cancel, 6.67 up here. Simplify the rest, you have the distance to be 10 raised to the power 20 meters. Or in standard form, you can say 1 times 10 raised to the power 20 meters. It means the same thing. Okay, example 4, it says a planet has mass M1 and it's at a distance R1 from the sun. A second planet has mass M2, which is equal to 10 M1, and it's at a distance of R2, which is equal to 2 R1 from the same sun. Okay, now determine the ratio of the gravitational forces experienced by the planets. All right, so let's write our parameters again. So we are told here that in this case that we have, okay, this is not part of our solution. Take this away. All right, so we are told here that M2 equals 10 M1, okay, and then in the question we also told that R2, which is the distance between the second mass and the sun. So R2 equals to 2 R1, we are given that. And then we have to determine the ratio of the force F1 to that of F2. Okay. All right. So this is what we have to find. F1 ratio F2 equals to unknown. Now, ratio simply means division. So when we break this down, we also mean to F1 ratio F2 also means F1 divided by F2. All right. And F1 by formula would be G multiplied by mass of the sun times the first mass over the distance between the sun and the first mass. Okay, for F2 it will be G multiplied by mass of the sun times the second mass all over the distance between the sun and the second mass, which is R2 in this case. The first one is R1. So the expression here, the the expression here is for F1, while this equation here is for F2, where the M1 represents the first mass, the R1 represents the distance between the first mass and the sun. Okay, and then the M2 represents the second mass, and the R2 represents the distance between the second mass and the sun. Now, when you go further to simplify this, division changes into multiplication sign, and when that happens, the fraction reverse their position. So the R2 square comes up, while the GMS and M2 come down here because of changing sign. And then in that case, M1 MS cancel MS, and G cancel G as well. Okay, so GMS has cancelled GMS here. That means the mass of the sun up and the mass of the sun down cancel out. G up and G down cancel out. So we are now left with M1 and R2 square at the numerator, and we are left with R1 square and M2 at the denominator. And when we multiply the numerator, we have M1 R2 square. When we have the denominator multiplied, we have M2 and R1 squared. Okay, now going forward, now you will remember from what was given to us in the question that M2 equals 10M1. What that simply means is wherever we see M2, we remove and replace it with M1. The same thing for R2 equals to 2R1. Wherever we see R2, we remove R2 and replace it with 2R1. So coming here now, we already have M1 R2 square and M all over M2 R1 square. So here now, we have M1. Now our R2 is actually 2R1. So we remove R2 and replace with 2R1, all still squared. The square still remain, but the R2 give way for 2R1 based on what we have here. So we now have M1 open bracket 2R1 close bracket the all squared for the numerator, and then for the denominator, remember again that M2 is 10M1. So wherever we see M2, we replace with 10M1. So here initially we have M2, then we replace M2 with 10M1. So we have 10M1 here, and our R1 square still remain. Now if you observe very well, you will see that M1 at the denominator down here can cancel M1 up here. So M1 cancel M1. R1 square also we cancel R1 square. But before we do that, let us simplify further the numerator. At the numerator, we could see that 2R1 is squared. So we need to expand that. That will now be 2 square R1 square, and that's what gives us this. So 2 square is 4. That's why we have 4. And then R1 square remains R1 square. Our M1 still remains there. So eventually we now have at the numerator 4M1 R1 squared all over 10M1 R1 squared. Now we can now say the M1 R1 squared at the numerator cancel out the M1 R1 squared at the denominator, so that we are now left with 4 over 10. And when you reduce that to the lowest fraction, you have 2 over 5, or when you change your division to a ratio, that will be 2:5 or 5:2. Any of this is correct because the question did not specify how the ratio should be arranged. You only say determine the ratio of the gravitational forces. So if you write 2:5, you're still correct. If you write 5:2, you are also correct. Okay, so let's take one more example and then we wrap it up with that. All right, so this question says, example 5 says, the force of attraction between 2 point masses is 10 raised to the power 4 Newton when the distance between them is 0.18 meters. If the distance is reduced to 0.0 meters, calculate the force. All right, now let's cut our parameters out. Let's take out our parameters again. F1 will now be 10 raised to the power 4 Newton. We have to find the second force, which is F2, and that is unknown. I've made the force here, so it's unknown. R1 is given to be 0.18, that's the distance. meters. But now it said if the distance is reduced to 0.06, now that our R2 now is given. If R2 is now 0.06 meters, we have to determine the force. This formula still applies here, that F1 R1 square equals to F2 R2 square. Then we substitute the values. Our F1 is known to be 10 to the power minus 4 multiplied by our R1, which is 0.18 squared, okay? And then F2 is unknown, and our R2 square is 0.06 squared. So when you simplify these, you have your F2 to be 0.0009 Newton. All right, so this is where we shall be drawing our curtain today. Thank you for listening. They are coming your way again. Bye for now.